So this is Laplace's equation, and we're back to chapter 2, this is section 2.5.1. Once again, you haven't missed anything. We were in chapter 12. Now we're back to section 2.5.1. We want to go back to traditional separation of variables to solve a very important PDE known as Laplace's equation. So Laplace's equation, basically, you can think of it as a steady state problem. One way to motivate it is, for example, consider the heat equation in 2 dimensions. And let's look at the steady state equation for the heat equation in 2 dimensions. So in 2 dimensions, the heat equation looks like this. I have partial U partial T equals K times the second partial of U with respect to X plus the second partial of U with respect to Y. This is the 2-dimensional part, right? Last time we looked at the heat equation, we only looked at the 1-dimensional version without this part. And now I want to look at the 2-dimensional version. So we have in the 2 spatial variables here, X and Y. So now assume U is not a function of T, and we get this equation. Finally, divide both sides by K. And so we get, here's the 2-dimensional Laplace's equation. You can also motivate this with the 2-dimensional wave equation, looking for its equilibrium position. And there's many ways to motivate Laplace's equation. It's very famous. So the Laplacian, or the Laplace operator, or the Laplacian, I should write that down somewhere. The 2-dimensional Laplace operator is this operator right here. So remember here, the input is this function U. The output is this, scalar here, the second partial of U with respect to X plus the second partial of U with respect to Y. And this can be shown to be a linear operator. So what does that mean? L of U1 plus U2 equals L of U1 plus L of U2. And L of any constant C times U equals C times L of U. So this can be shown to be a linear operator. And we have reserved notation for it. In Calc 3, you might see this Noblos squared for the Laplacian. More commonly in PDEs, it's written this way with a big capital delta here. And this is typically in PDEs how we write Laplace U. And that thing is called the Laplacian, is what folks will refer to it as in PDEs. So it comes up in many places. It's just a fundamental PDE that, many people in PDEs, you tend to pick a PDE and then study that for the rest of your life. So I'm a Laplacian person. That was what I studied. And so one particular application that's slightly relevant to me is the application to electrostatic equilibrium. So here, if we have an electric vector field, then in steady state, Maxwell's laws implies that the electric vector field is proportional to the gradient of the electric potential. So it's this change in electric potential that results in the electric vector field. The lower dimension. So you can current this to, you can relate this to current and different phenomenons involving current, as well as, have applications to things such as rust prevention, which is a type of movement of electrons. Anywho, so yeah, the Laplacian is very important in many different fields. You'll find different applications. So let's talk about solving the actual PDE just from a straight mathematical point of view now. So we want to start by, with a PDE, the things that can make a PDE complicated is the domain, the type of functions you're working with, the type of data you have, of course, not to mention the actual PDE. So here we're going to look at Laplace U equal to 0. And we're going to look at a 2-dimensional, what we call a rectangular domain. So here, I don't know if you've seen this notation before, but here I have x comma y is in this. So this thing here, this notation implies that x is between 0 and L, and y is between 0 and h. And typically something like this might be referred to as a rectangle. And you can see here, x is between 0 and L, y is between 0 and h, and this is the domain we're looking at. And on the boundary of our two-dimensional domain, so for example here, you should think here, so here this is when y equals 0. So when y equals 0, we're on the x-axis. And so when y equals 0, our boundary condition there is u of x comma 0 equals f1. And it's purely a function of x there. And similarly here we have when y equals h. So that's the top boundary up here. We have a boundary condition there. U of x comma h equals f2 of x, and at that boundary when y equals h, u is purely a function of x. And similarly here, we have boundaries on the left and right side. So here for u of 0 comma y, here we're assuming x equals 0. And so that, and y is between 0 and h. So that puts us on this left side. And the boundary condition there is u of 0 comma y equals g1 of y. On that boundary, u is purely a function of y only. And then we have the right side. So here we're assuming x equals capital L, which is the right side here of our rectangle. And then we have a boundary condition there that's purely a function of y. And so keep in mind, this is a steady state calculation, so there are no initial conditions. That's one thing that can be slightly confusing right now when we talk about Laplace, is we're so used to having a time component from the heat equation and the wave equation. This is different. Time here is not a factor. This is a steady state calculation, essentially. So there's no initial condition. An initial condition is, the behavior of the function at some initial time, typically t equal to 0. Here, time is not a factor. There's no initial condition, but we do have boundary conditions. And since this is a two-dimensional problem here, we have this, 4 boundary conditions here.
Dr. Bott?
Yes.
So just to be clear, u is not a function of t at all. It is completely time invariant.
Right.
Okay.
So now, this is complicated here with so many boundary conditions. And certainly we're not getting any of our vector space stuff from the boundary conditions if these aren't trivial. So how do we solve it? We're going to try and decompose the problem into 2 PDEs using the fact that the Laplacian is linear and that we can find 2 solutions, add them together to find a solution to the main problem. Evan?
So I've heard the Laplacian be described as the divergence of the gradient of the function. What is a good physical or geometric intuition of what the Laplacian equal to 0? What does that mean? Does it mean every point is a saddle point, or does it mean something else?
Yeah, I don't really know. That's a good question. I've been spending a long time trying to answer that question. So that's a great question, and which I won't answer. So, but if you find out, let me know. I want to know. This is only the 2-dimensional Laplacian. What about the 3-dimensional Laplacian? That's what I worked on. So that's what I want to know. So look at how we decompose the problem. I've got a U1 and a U2. Yeah, let's everyone look on the internet. I'm sure it'll tell us everything we need to know. So here, look at the sneakiness on the boundary conditions. So let me show you the other one. Right, me too. What we've done is we've decomposed the non-homogeneous boundary conditions. So we have this pair right here, which you can see we've put on this first problem. And then we have this second pair of boundary conditions here that we've put on this other problem here. And in both cases, what's nice, how is this helpful? Well, really the thing we want are the trivial boundary conditions. Because now we can start to use our theory again. Now I can start to say, well, if you look at the set of functions, and you've probably never heard me say this phrase before, so this is the first time. If you look at the set of functions that satisfy the PDE and these trivial boundary conditions, they form a vector space. And that's kind of a new concept that I'm just introducing right now. Obviously, I'm just kidding. And on the other side here, you get the same setup, which we like mathematically. Look, the set of PDEs that satisfies, the set of functions, excuse me, that satisfies the PDE and these trivial boundary conditions, that forms a vector space. And so now it's kind of game on. You know, here, let me use this PDE and these trivial boundary conditions to solve it using separation of variables. And then let me use the remaining information to find the coefficients. Then after that, let me use this remaining information to find the coefficients. So we're treating one pair of boundary conditions, kind of treating them like initial conditions. So here, this is almost like a heat equation setup where we've got, you know, a set of trivial boundary conditions, and then we have some functions that are like initial condition, but they're not an initial condition. It's the other set of boundary conditions. And so, you know, we do that twice. Here, it's the same idea. We use the PDE and trivial boundary conditions to do a separation of variables, but then we always need more information to find the coefficients. There'll be two unknown coefficients as a second order. There'll be four unknown coefficients, but hopefully that first PDE will allow us to find the first two. But here, we then use this information like an initial condition, the other pair of boundary conditions. So let me show you. We're going to go back to something familiar. We're going to go back to separation of variables, okay? So back to traditional separation of variables. Here, let's first solve the system for U1. And then we'll solve the system for U2. And so this should be somewhat review, I hope. You know, it's the usual story. The set of functions, this should be plural, set of functions, I'll fix that, that satisfy the PDE and boundary conditions, these trivial boundary conditions, form a vector space. So let's try and solve it. As always, I assume U of xy, here's my separation of variables assumption. U of xy equals f of x times g of y, not g of t. So this is the part I want you to be, you know, be aware how this is different from the heat equation. It's very similar in a lot of ways, but then this is where it's different. We don't have a time domain problem. Remember, x is a spatial variable, so is y. Okay, so here we go. I plug it into the old Laplacian equation, Laplace's equation, del u equals 0. So I get f double prime of x times g of y plus f of x times g double prime of y equals 0. I'm going to take one set of these and move them over, and then put all the functions of y on one side, all the functions of x on the other side. And then I put the minus sign with the y variable here. And we say, you can prove it mathematically, or you can even argue that the only way we have a function of y equals a function of x is if they're both equal to a constant. So we set it equal to this constant negative lambda. The minus sign there is introduced for mathematical convenience. And so now we have two problems. I don't talk about time domain and space domain anymore, so be careful. They're both space domain problems. So we have the x variable problem and the y variable problem, or sometimes it's called the f equation and the g equation, depends what letters you're using for your separation of variables. But yeah, so now we use that kind of language to distinguish between the two different ODEs that we have now. And using these trivial boundary conditions up here. So let's think this through. For example, here, so let me clear some space. So for this first boundary condition, so here, remember, we're making the assumption that u equals f times g. So this says f of x times g of y. We're making the assumption u equals f of x times g of y. So this says f of 0 times g of y equals 0. And now I claim g of y cannot be equal to 0. G of y cannot be identically equal to 0. If g of y equals 0, then we get a trivial solution. If this g of y equals 0, then we get a trivial solution, which is not allowed. So I claim g of y is not 0, so we can cancel this. And so you get a boundary condition f of 0 equals 0. And similarly here, this other boundary condition, u of 1 at capital L of y equal to 0, that gives us f of capital L equals 0. It's the same stuff, but it's important to think it through and just think about those little details, because it's always the little details that later come back, and we have questions about those little details. So yeah, we're just following just all the basic steps of separation of variables, just using our assumptions, plugging it into what we've got, and just doing the math. And so yeah, now we get two equations. And this f equation actually is familiar to us. This is the identical, it's the same as the space domain problem or the eigenvalue problem. It's the eigenvalue problem here, as when we did the heat equation with trivial Dirichlet boundary conditions. So this is the same. We're expecting to see a sine series here, at least in the x variable. So here we can show that the only interesting case, the only case where we get non-trivial solutions is if lambda is greater than 0. And as before, we use our ODE technique of assuming f of x equals e to the rx, and then we plug that into the ODE on both sides and solve for r. And so here we can show that the solution gives us this sine function. So here I'm not going to go over all of that separation of variables stuff that well that we did for heat equation. We get complex roots, but then we use Euler's formula, and we take a linear combination with Euler's formula to get a sine and cosine. But then the boundary conditions make the cosine term disappear and you get the sine term. And the second boundary condition allows us to conclude that, square root lambda n capital L equals n pi. So then we can solve for square root lambda, first lambda sub n. And you get the usual n pi over L quantity squared. So please take a look at heat equation, separation of variables if you need to review. I'm sure, we've seen it so many times. So I skipped all that. I didn't want to make you go through that again. So now we have to solve the G equation. So this is where something different happens and something, we do some slightly different mathematics. Here, the G equation, again, we let G equal e to the Ry. That's the standard approach here for this type of ODEs. The G equation is a second order ODE though. And so we plug in, you get R squared equals lambda sub n. In this case, we already know what lambda sub n is. We solved for lambda sub n in the previous slide here. So here we're not looking for, we already know what the eigenvalue is. So here I know R squared equals n pi over L squared because we know what lambda sub n is. So here, first I cancel the e to the Ry. And then we replace lambda sub n with n pi over L quantity squared, which is what we'd calculated on the previous slide from the F equation. So you take the square root, you get R is plus minus n pi over L, and you plug it back into the exponential function. So here, I now plug this back into here. So we found a basis of the solution. We could write the solution to the G equation as a linear combination of e to the n pi y over L and e to the minus n pi y over L, but we're not going to. What we would like is a basis functions that disappear at the endpoints. That will make it easier to apply the other set of boundary conditions. Because our other set of boundary conditions, we have a boundary condition that's like U1 of, what is it? Like, at the other two boundaries are at 0 and H. And so we'd like the thing to disappear at 0 and H so that we can then do a Fourier series type of trick. Just like in the heat equation, when you let t equal to 0, that exponential term disappeared and you got this Fourier series. So here we're trying to do the same thing. Like we know through superposition, when you sum this part, like here, what's going to happen is we're going to multiply this function by some other function, g sub n. We're going to multiply this by some function g sub n. That's the worst letter G ever written. Let me try again. Yeah. Okay. So we're going to multiply this by some function g sub n and do a big superposition. What we would like is if the g sub n, when you let y equal to 0, if the g sub n disappeared, all you're left with then would be a Fourier sine series. And so we want this term to disappear when y equals 0 or when y equals capital H, so that the series we have left is a Fourier sine series. So then we can use orthogonality to find the coefficients. We got this really nice thing happen with the heat equation that when you let t equal to 0, that exponential term just went away. So it'll make sense when I get to it. So just trust me. But yeah, so this is it is a basis, but it's not mathematically convenient. So now we actually take linear combinations. And this is one of the reasons we reviewed hyperbolic functions way back at the beginning of the semester. So you might remember from Calc 2, we can define the hyperbolic cosine as e to the x plus e to the minus x over 2. Just to make it more complicated, I went with theta. So here, hyperbolic cosine, cosh of theta is e to the theta plus e to the minus theta over 2. And we can define the hyperbolic sine as e to the x minus e to the minus x over 2. Here I use theta, so here I have sinh of theta is e to the theta minus e to the minus theta over 2. So, don't let the notation mess with you. They're just, nice ways of writing this pattern of functions, the sum of e to the theta and e to the minus theta, and the difference, that comes up a lot. So the Cosh graph kind of looks like a parabola, and the Cinch graph kind of looks like x cubed graph, sort of. Anyway, those graphs are terrible. So basically, I can now claim that Cosh n pi y over L. So by adding these two and dividing by 2, I get Cosh being in that family of functions. And by subtracting one from the other and dividing by 2, I get Cinch. And these are linearly independent, and we have 2 of them. So this is also a basis. It's also a basis for our solution to our G equation. So we could use this linear combination of Cosh and Cinch as a general solution. But this is not quite what we want, because we want something that'll completely disappear. One term will disappear when y equals 0, and the other term will disappear when y equals capital H. So here I still don't have something that's disappearing when y equals capital H. So, if you're like, what the heck's going on? I think that's the right thing to think about right now, because it's hard to know what the end goal is, but there is a legitimate end goal here. And when you see it, then you'll say, oh, okay, I guess this kind of makes sense. So here we need to use one final identity, a hyperbolic trig identity. Okay, here's one final math trickery, and I'll show you something nice that happens. So we have this hyperbolic identity. It's similar to the sum and difference type of identities that we have for sine and cosine. Here, what you should really see is a difference. The n pi y over L will distribute to each term. Okay, so the n pi y over L, that's common to both terms. So at the heart of this here, you have a difference. This is sinh of n pi y over L minus n pi h over L. And now, just like we have sum and difference formulas for sine and cosine, we have sum and difference formulas for the hyperbolic sine. I don't remember if I put it on the review sheet, I can't remember, but it's the same idea that we have these identities. So using identity for sinh, we can rewrite sinh of n pi y minus h over L. And so this is the part now. Here it's going to be sinh of n pi y over L. So this is a basis element times cosh of n pi h over L. This is a constant, because h is a constant, L is a constant, pi is a constant, n will be some number, it's our parameter. Minus, I have cosh n pi y over L, that's another basis element. Times, and here I have a sinh n pi h over L, that's a constant. Again, L, H, and pi are all constants, n's a parameter, n will be, a number 1, 2, 3. So what we have is a linear combination of the basis elements. So this, again, is in the space of functions. If I can, and we can show that sinh n pi y minus h and sinh of n pi y, we can show these are both linearly independent and they both span the same space. Sinh n pi y, that's got that term covered. The other term we need is the cosh n pi y, and that's buried in here. That's buried in the sinh n pi y minus h term, secretly has the cosh n pi y over L. So between the sinh n pi y over L and the cosh n pi y over L, we've got a basis for the entire set of solutions of the G equation. And so this is how we want to write the general solution for the G equation. So what I want to do now is just go back one slide here and just big picture. Here, we should have written it as a linear combination of these functions. We said, oh, that's not nice. That's not mathematically convenient yet. What we want are terms that'll disappear when you plug in 0 or h. So then we said, okay, so let's try cosh and sinh. And here we could have used this, but again, this is not quite that nice, because again, this is okay. This will disappear when y equals 0, but the cosh term is a problem. That doesn't disappear. If you let y equal 0, cosh equals 1. If you let y equal h, you'll just have some number there. So it's not quite ideal. We don't like this cosh term. So finally, let's use a hyperbolic trig identity. And based on the identity, we end up with this basis that does use the sinh n pi y, but has this this other term that happens to be a linear combination of the sinh n pi y and the cosh n pi y. So it still spans the space. And these things are linearly independent. So now we write our solution this way. So this is finally what we end with. And what's nice? So here's what's nice. When you let y equal 0, this term will disappear completely if you let y equal 0. If we let y equal capital H, I plug in a capital H here, h minus h is 0, sinh of 0 is 0, this term will disappear if you let y equal to h. And that's what we're going for. We wanted to set it up so that one term will disappear when we plug in y equal to 0, and the other term will disappear plug in y equal to h. This will allow us to find the coefficients. So here, let me show you now how this helps us. So here we can now make the product solution fn of x times gn of y. There's no t variable here. They're both spatial variables. So here is what the superposition solution looks like. Here's the solution to the f equation, and it's not a hyperbolic function. Here's our x variable. And here is the other part. So this was our G equation solution. So there's the sinh n pi y from the G equation. There's the sinh n pi y minus h over L from the G equation.
Dr. Bott, just
Yes.
a notational thing. U1, that's not the solution to just our first problem.
No, that's a typo. That's a typo. That should just be a U.
Cool. Thank
So
you.
I need to fix that. Thank you. So yeah, this sub 1 shouldn't be here. So okay, so let's just for 1 second now think about why did all these manipulations with the G equation help us? So look what happens now if we let y equal h, for example. So let me write that. So look, if you let y equal h, then this term right here disappears completely because you get sinh of 0, which is 0. So this term disappears. And here, if I plug in a y equal to h right here, sinh of n pi h over L is just a constant. So I can think of this whole term here, a sub n times sinh of n pi y h over L. I can just think of that as a new a sub n tilde. Because it doesn't, the y has been replaced with h and it's got no variables in it. It just has the parameter n. It's just a number that depends on n. Let's just call it a sub n tilde. And then what you have is a sine series, a Fourier sine series. Okay, so let me show it to you explicitly. I just wanted you to imagine it first. And so now let me show you explicitly here. Look, if we plug in a 0 for y, let me show you, if you plug in a 0 for y, Plug in a 0 right here. Sinh of 0 is 0. This term disappears completely. And we've plugged in a 0 right here. So I'll have sigma b sub n sinh n pi times negative h over L sine of n pi x over L. And that's what we have here. Sigma b sub n sinh negative n pi h over L sine of n pi x over L. The a sub n, the sinh of n pi y over L disappeared when we let y equal to 0. That's a nice thing. And here, this whole term is just a constant that depends on n. So let me rename it b sub n tilde. So I'm calling this whole thing now, I'm just going to rename it b sub n tilde. And so if we step back and take a look, the theories we have now, well, that's a sine series equal to F1. So using orthogonality, I can find a formula for b sub n tilde. And finally, b sub n tilde is this. It's b sub n times a constant. So if I divide both sides by sinh of negative n pi h over L, then I'll be able to solve for the b sub n right here, which is unknown. And so finally here's my formula for b sub n. It's the 2 over L, it's the usual formula for the coefficient from a sine series divided by that extra constant. So we have this extra term here. We're dividing by that down here. So remember, this is a constant, but it does have an n in it. So, we'll have to think about, we always have to think about convergence. So, but let me not worry about that right now. And if you plug in the h, if you plug in for replace y with capital H, then the b sub n term, because the b sub n term is times sinh n pi y minus h. We replace y with capital H, you get sinh of 0. The b sub n term disappears. We only have this a sub n term left. And here the y has been replaced with capital H. So bear with me here. I'm just going to go back one slide. I want you to see it. I should have probably repeated that equation. So right here now, replace this y with a capital H. This term disappears. And here we also have a capital H right in here. So I'll have U1. Oh, wait, I think that was a U1. So that was a U1, but it's I guess it's the U1, like our first solution for our, that's what I mean by the U1 here. That's not entirely a typo. It's U1, like it's the solution, because we've got the decomposed problem where we have U1 and U2. So this is the U1, but not the product solution U1. Yeah, it's not great notation, but whatever. I don't want to put other weird notation in there. Anyway, I hope you all know what the heck I'm talking about. So yeah, we can find using, again, you get a sine series. And again, Aubrey, it's just a matter of when you get trivial solutions. It goes back to the heat equation again. It's just about when you have trivial solutions and when you don't have trivial solutions. Here, the F equation problem is the same as the space domain problem as in the heat equation. So it's just that in the lambda, those other cases, you just get trivial solutions because of the boundary conditions, yeah, I don't know, there might be a physical reason, but I don't know. Someone should explain it to me.
But
One
like
of you physical scientists should explain it to me.
But you could go through with complex lambdas and still find that they're trivial.
Well, I don't know why they don't look at complex lambdas, or maybe we will when we look at the Fourier transform. That's when complex stuff comes up, but I don't know why we specifically look at real eigenvalues. I'm not sure.
Okay.
So now again, when you replace the y with an h, this sinh n pi y over L, that becomes sinh n pi y, n pi h over L, that's a constant. And so I replace all of this mess with a sub n tilde, and then if you step back, you go, oh, this is a sine series, and I can solve for a sub n tilde, but then if you divide by the constant, we can solve for a sub n. And so now we've solved the U1 problem. So remember here, we have these two systems. So here we've solved the U1 problem. And now, double the fun, we have to solve the U2 problem. And here, again, it's going to be very similar, except the role of the G equation and the F equation are going to be reversed now. Because now we have the trivial boundary conditions when y equals 0 and y equal to h. In the previous case, we had non-trivial boundary conditions when y equal to 0 and y equal to h. So you'll see it'll look very similar. We'll actually get a solution that looks identical to the U1 equation, but the role of the x and y variables are reversed. If you take the U1 equation, replace all the x's with y's and replace all the capital H's with capital L's, you basically get the same type of solution. Because here in the U1 equation, here's where we have our trivial boundary conditions. And here's, so they're we've sort of flip-flopped the role of the x and y variable here. They've here's where you have the non-trivial, so you sort of flip-flopped them. So here, let's do separation of variables again for the U2 problem. So here we go. Here's the U2 problem. So just a comment, if you're reading the book, here we separated this into 2 problems. The book separates it into 4 problems. So and it's not necessary, but the book will have like this. It'll have 4. So it'll have U1, U2, U3, U4. And it'll have at any one time, it'll just have one of the things be non-zero and the other 3 be non-zero. And then it adds the 4 solutions together. So here, what I did was I did a slightly more compact approach. I combined these 2 in one problem, make the other 2 trivial. Okay, so if you're reading in the book, they'll break it up into 4 problems. Maybe that's good review for you. So here, again, we're going to use separation of variables on U2 now. And you get basically the same thing, except it's the G equation that has boundary conditions. Because here, when we do separation of variables, for example, this first equation, for example, will become, so remember, I'm assuming U2 equals F times G. So this will become F of X times now G of 0 equals 0. If I assume F of X is 0, then we get a trivial solution. So F of X can't be 0. So G of 0 must be 0. That's where that boundary comes from. And then the other boundary condition, U of X comma H equals 0, gives us G of H equals 0. And so you see how this is flip-flopped. And here for the F equation problem, we just have F double prime equals minus lambda F. And we've separated it, setting the F part equal to minus lambda, just like we did in the previous equation. So here we consider the case lambda less than 0. And I'm going to write lambda this way because I'm assuming lambda is negative. And so now if you take the square root, we get this. And so we get, it's very similar to the F equation. I mean, it's basically identical, except in the F equation, we have it's equal to minus lambda. In this case, we have it's equal to lambda. In the F equation, you get trivial solutions if lambda is less than or equal to 0. In this case, you get trivial solutions if lambda is greater than or equal to 0. It's the same problem, just off by a minus lambda. And that we artificially stuck in anyway. So you get the same solution, basically, except instead of a capital L, which we're so used to, this is a capital H. Remember, this is not a time domain solution. We solved basically the same problem, but just in the y variable. And here, you know, so y goes from 0 to h. So instead of n pi over L, we have n pi over h squared. And with the F equation now, it's the same procedure as before. We know now what lambda is. So here, r equals square root lambda. We can replace this r right here with square root lambda. So you get e to the n pi x over h, just like with the G equation. And just like with the U1 solution, we write it as sinh of x, sinh of n pi x minus L, because we want terms that'll disappear when x is equal to 0 and when x is equal to L, so that we end up with a sign series so we can use orthogonality to solve for the unknown coefficients. So here, if you look at U2 and if you look at U1, they're basically the same, except you have to flip the x's and y's, h's and l's. But it's the same procedure because we have no time domain problem here. We just have two space domain problems. And so using orthogonality, we can solve for the coefficients. Oh, I guess I'm over time. And so now here is the big solution, the big super mega solution that's combining U1 and U2. So here's U1. Whoops. Here's U1 plus here's the U2 solution. And here I put all the formulas for the coefficients just so you have the whole thing in one place. So if you thought it was awesome in one variable, it's even better in two variables. So here, the most important thing I want you to keep in mind is this is a steady state solution. There's no t variable. And so, you know, once we've gone through this calculation, we're not doing it again over and over again. But, you know, once, just like with heat equation and wave equation, once we've done it once, we can just kind of, now we can know to skip to the answer kind of a thing. But of course, you should review the separation of variables for the umpteenth time and review all those little details. But it's, you know, it's mostly algebra. So yeah, so I just talk about, you know, some final issues here, which we'll talk about next time, including convergence. And then we'll talk about some analytic results that we can get. So I'll pick it up at this slide next time, and we will look at a Laplace's equation on different boundaries and use polar coordinates, do separation of variables in polar coordinates. All right, everybody, I'm going to stop right here.